All right, this is our 9th session on simple harmonic motion. Just like we've been doing, we're going to start with the multiple choice. Go ahead and read through and try to answer the multiple choice. After you've done that, hit play on the video and I'll explain it. So, first one. An object is executing simple harmonic motion. What is true about the acceleration of this object? So, before we even jump into these things, let's talk about what happens in simple harmonic motion and what our example of simple harmonic motion is. A mass on a spring is simple harmonic motion. So let's say we have a spring holding a mass. That thing is going to bounce back and forth. Now here are a couple alwayses for simple harmonic motion. For simple harmonic motion, the object always moves because of a restoring force. All that means is that the force pulls the object back in the opposite direction of So it's going to pull it back in the opposite direction of the displacement. So when we talk about a mass on the end of a spring, we see that the force of the spring is equal to negative k times x. What this negative sign means is that the force is opposite the displacement, where x is the displacement. And k is the spring constant. Now, when we pull this mass back or forward, if we displace the mass out to here, this is the equilibrium position where the net force is 0. This is one amplitude out. When we're displaced this far, I have a maximum force. It's pulling me back towards the equilibrium position. The object's going to move back this way, but as the x gets closer to equilibrium, the size of the force gets closer to 0. So when we're back at equilibrium, the force is 0. We're moving, so we move past equilibrium quickly, and we come back to another amplitude, would be the negative amplitude, and the force here would be negative k times negative a, would be ka, and that force would push us back to equilibrium. So, because this force depends on the displacement, as do all restoring forces, we have maximum force, maximum acceleration, at an amplitude. And since we're here, we'll go ahead and define an amplitude. Amplitude is maximum displacement from equilibrium. So we pull it out to an amplitude. We're going to have our max acceleration and our max force, but we also, at the amplitude, turn around. max amplitude is the turning point. That's part of why we have our big acceleration. But what that means is that because we're turning around, the velocity at the maximum amplitude is 0. We are temporarily at rest at the maximum amplitude. The other thing that happens at the maximum amplitude is that we're storing all of our energy as we're storing our maximum amount of potential energy. Or our potential energy, doesn't have to be spring potential, is a maximum at maximum amplitude. So these things occur at our maximum amplitude, at our maximum displacement. The other interesting point in simple harmonic motion is the equilibrium position. At the equilibrium position, the displacement is usually 0. We call it 0. We talk about displacement from the equilibrium position. So the displacement is a minimum. The net force is 0. That's part of what it means to be at equilibrium. And the acceleration is 0 at this equilibrium position. The next thing that happens at the equilibrium position is that the object has its maximum velocity, its maximum speed, because it's going to be going in two different directions, at the equilibrium position. And what we see is because it has its maximum speed, because potential is minimum, the object is going to have its maximum kinetic energy. At equilibrium. And at equilibrium, in addition to the net force being 0 and the acceleration being 0, the potential energy is a minimum. So at this equilibrium position is when all of these things happen. Those are our interesting points for simple harmonic motion. What happens at an amplitude and what happens at equilibrium. Our other example of simple harmonic motion is pendulum. A simple pendulum is simple harmonic motion. For a simple pendulum, we have the mass hanging down right here. We displace that mass just a little bit from the equilibrium position, and part of the weight pulls it back down. So this spot down here would be the equilibrium position. We represent that by saying it's the net force equals 0 position. That's our shorthand for equilibrium. And then for small angular displacements, this is simple harmonic motion. This would be at an amplitude of theta. That's how we measure amplitude for simple harmonic motion. So the same things are true at equilibrium and at maximum amplitude for a simple pendulum as they are for a mass on a spring. So let's go back to question A. Question 1, rather. Question 1 has two correct choices that we could select. The acceleration is a maximum when the object is instantaneously at rest. So, we talked about this. The acceleration is a maximum at maximum amplitude. The object is turning around when it's instantaneously at rest, also at maximum amplitude. That's going to be at the same spot, so that one's correct. The acceleration is maximum when the displacement of the object is 0. This is good to keep in mind. Displacement is always going to be measured from the equilibrium position. So, the acceleration is going to be a minimum when the displacement of the object is 0. The acceleration is a maximum when the displacement is a maximum. We said max force at maximum displacement. Especially because when we look at this, the force acting on my object, in the case of a spring at least, depends on my displacement from that equilibrium spot. So that's true. The acceleration is maximum when the speed is maximum. Well, A and D cannot be both true. And the acceleration is 0 when the speed is a maximum. Well, that's also true. So there are going to be 3 true answers here. Because the acceleration is 0 at equilibrium, and at equilibrium we said the object is moving at maximum speed. It has its biggest velocity. Alright, number 2 shows a graph of periodic motion with an amplitude of 2 centimeters and a frequency of 5 hertz. Alright, so there are some words in here that we need to look at and make sure that we know. Amplitude of 2 centimeters. What this means for amplitude, amplitude is the maximum displacement from the equilibrium position. This means that my maximum displacement will be plus or minus 2 centimeters. We're going to oscillate around the equilibrium position. Sometimes we have a positive amplitude. Sometimes we have a negative amplitude. So looking at these right away, I can eliminate A, because that shows me with a maximum displacement of 1 and the minimum displacement, a maximum displacement of 1. B is correct, C is correct, D is correct, E is not correct. So, other words that we need to know from this sentence, we need to know what frequency is, and then its corollary, the period. So frequency that is the number of complete oscillations per second, or number of complete cycles per second. So here, our frequency is half of a hertz. That means in 1 second, we get half of a cycle. That's measured in hertz. Which is 1 cycle per second. And the corollary is the period. For period, we use a T, Latin reasons, I assume. The period is the number, well, I won't say that. It's the amount of time per one cycle. So if the frequency is the number of cycles per second, the period, just time, is the number of seconds per cycle. So the period is the inverse of the frequency. I like looking at the period better on graphs like this because we can see an entire cycle much easier than we can see what's going on in just 1 second. So in this case, the period is going to be 2 seconds per cycle. We'll go back and calculate that. The period is 1 over the frequency, so that's 1 over 0.5 hertz, giving me 2 seconds per cycle. So what we're going to do is we're going to look through these things that we've already decided that have the correct, and we're going to find the ones that also have the correct period. So let's look at this. A period is 1 complete cycle, so we're going to outline that in red. So this is 1 complete cycle here. That would be 1 complete cycle there. And here's 1 complete cycle. So looking at this graph, in order to complete 1 full cycle, period is 2 seconds. Looking at this graph, period is a little bit off of my graph, but if I had to imagine, I'd say that the period here is about 12 seconds. And then looking at D, the period is 3 seconds. So if I want the one that has a frequency of half a hertz or a period of 2 seconds, it's going to be B. All right, number 3. A mass M is attached to an ideal massless spring. When this system is set in motion with an amplitude A, it has a period of T. What is the period? The amplitude of the motion is increased to 2A. Here's the deal. When we're talking about period specifically, period for a spring is given by 2 pi on the square root of the mass divided by the spring constant. Now, if we're talking about a pendulum, the period is given by 2 pi on the square root of the length of the pendulum divided by the acceleration due to gravity. Now, what this means for a spring is that the period only depends on the spring and the mass, nothing else. So that means not speed, not amplitude. Not the weight, so not gravity. Only on the spring constant and the mass. Those are the only 2 things that matter. For a pendulum, period only depends on the length of the pendulum and gravity. So here, that means not amplitude, and not the mass. They're 2 completely different situations. So, if I have a mass on a spring and I increase the amplitude to 2A, that's going to do nothing to my period. That remains the same. It's completely unaffected by the amplitude. Number 4, in simple harmonic motion, the speed is the greatest at that point in the cycle when? Okay, one thing we need to see, speed is the greatest at at equilibrium. Some other things are true at equilibrium. One of them, the biggest one, is that my position is 0 because we always measure that position from equilibrium. That means the force is equal to 0. The restoring force is equal to 0. That means the potential energy is equal to 0. Those things happen at equilibrium. So, the speed is greatest when the magnitude of the acceleration, since the force is 0, the acceleration is 0. So I have a small acceleration, no potential energy, small acceleration, large kinetic energy because it's the greatest speed, and kinetic energy is 1/2 mv squared, and the displacement is a minimum. The only correct answer is A. Number 5. The figure shows the position as a function of time for a system undergoing simple harmonic motion. Which graph represents the velocity of this system as a function of time? So we've got a graph, and we're asked to look from position to velocity. So a couple of things are going to be very, very important for us. One, every time we see a graph, we better look at what the slope represents and what the area represents. So here, the slope is going to be position over time. That's velocity. And then here, the area is position times time. That is nothing. So we don't have to worry about the area because it's not a thing. But the slope is the velocity. So that's very helpful. Let's look at some things that we see right away, analyzing this in terms of the slope. So in terms of the slope, we'll do little tangent lines. We're going to use a small straight line to look at the slope. That's a positive slope. That's a negative slope. And that's a 0 slope. So if we're talking about a position versus time graph, this shape gives me a positive velocity. This shape gives me a negative velocity because slope is the same thing as velocity in each of these cases. So another thing that's useful to keep in mind when we're looking at position versus time graphs, this is kind of a bonus. Any shape like this is positive acceleration. Any shape like this is negative acceleration. And any shape like this is 0 acceleration. That's kind of helpful. So think of it this way. That's a negative slope. That's a 0 slope. That's a positive slope. So if we're looking at a position versus time graph and we go negative, 0, positive, it's overall positive change in my velocity. Likewise, if we look at the negative acceleration, when the frowning face, we start off with positive, we go to 0, we end up with negative. Positive 0 to negative is an overall negative change in my velocity, giving me a negative acceleration. I would say that understanding these things right here will get you a very far way in understanding a position versus time graph and getting any of the other graphs from it. So let's use a small straight edge and look at some really important points on this velocity, this position versus time graph. So here at the beginning, I have positive slope. Then it moves to 0 slope. Then it moves to negative slope. And then it moves to 0 slope. Which means we start off with a positive velocity. We go to velocity equals 0, get to a negative velocity, and we end down here with a velocity equals 0. So, at the very beginning, we should have a positive velocity. B is the only one that has a positive velocity at the very beginning. A does not, it starts off with a 0 velocity, it's just a repeat. C does not, it starts off with a negative velocity, and D does not, it starts off with a 0 velocity. But let's just make sure, just in case, that it works. So that shows a positive velocity, this shows a 0 velocity, that shows a negative velocity, that shows another 0 velocity. That's the exact same pattern that we saw up here in the position versus time graph. While we're on the subject of graphs, this is a special kind of graph. It's a sinusoidal graph, sine or cosine graph. So, what this graph tells me for position is the amplitude times the cosine and there are two different ways to do it. One way is to say that it's the cosine of 2 pi times the frequency times the time, or it's to say that it's cosine of 2 pi over the period times the time. But since those are inverses of each other, that's really just the substitution that we have to make. So, because it's a cosine graph, it's going to go, the cosine part it goes between 0, sorry, it goes between positive 1 and negative 1. That's part of the cosine graph. So that means overall my position goes between a positive amplitude and a negative amplitude. And then the 2 pi over the period tells how quickly we go between the positive and the negative. This is a good thing to know what the function of this graph is. May come up. Number 6. We have another graph that shows the position as a function of time, and I want to know which represents the acceleration of the system as a function of time. Okay, so to reiterate, on a position versus time graph, positive acceleration is concave up, or smiley face. Negative acceleration is concave down, or frown, particularly grumpy. And then 0 acceleration is any flat line. Sorry, not any flat line, any straight line on position versus time. So any one of those would be 0 acceleration. All right, so here what we see is a little bitty flat line right here. So that's 0 equals my acceleration. And then here at the top, we got a bit of a frowny face. That's negative acceleration. And then here again, we have a bit of a flat line. So 0 equals my acceleration. Here it's smiling at us, so it's positive acceleration. It's flat again, so I have 0 acceleration. rounding again, so I have negative acceleration. Then it's sloped down again, so I have 0 acceleration. All right, so let's look at our acceleration graph. I want to start off with 0 acceleration. So B is out, and C is out. And down here, that's negative acceleration. 0 acceleration. Up here, it's positive acceleration. Here, it's 0 acceleration. Down here, it's negative acceleration. That matches what we were doing. Part D does not. It shows me positive acceleration. It's a repeat of what's going on. So D is not correct. D is out. Correct answer for that one is A. Take a moment. In simple harmonic motion, when the speed is the greatest, select two answers. So we have speed is the greatest at the equilibrium position. So the net force is equal to 0. The displacement is equal to 0. The acceleration is equal to 0. All those things happen when the speed is the greatest. We also have potential energy. This is small. So potential energy is a minimum, not a maximum. The displacement is at a minimum. The magnitude of the acceleration is at a minimum, not a maximum. My answers there are B and E. Because greatest speed occurs at equilibrium. Number 8, the total mechanical energy of a simple harmonic oscillating system is, all right, if what's happening here is an exchange between potential and kinetic energy, then energy is conserved. Specifically, mechanical energy is conserved. When we say mechanical energy, kinetic energy plus potential energy is my mechanical energy. So that tells me that the sum of kinetic and potential energy must be constant if mechanical energy is conserved. So the total mechanical energy should be a non-zero constant. It should never, ever, ever, ever change. At equilibrium, kinetic energy is a maximum value and U is at a minimum value. At an amplitude, kinetic energy is at a minimum value and my potential energy is at a maximum value. They're swapping that maximum minimum value back and forth between each other evenly the entire time. Number 9, a mass on a spring undergoes simple harmonic motion. When the mass is at its maximum distance from the equilibrium position, which of the following statements are true? Maximum distance means that we have maximum force, because my force is equal to negative kx, and the bigger my x is, the bigger my force is. I have maximum acceleration, because acceleration is force over mass, so it's negative kx over the mass. Maximum force, maximum acceleration. And since it's maximum displacement, I have maximum potential energy, because potential energy for a spring is 1/2 kx squared. All of those things happen at the maximum distance from equilibrium position. That's what's maximum. That also means that the speed is 0. The object is turning around, and because the speed is 0, the kinetic energy is 0. So, which of the following are true? Kinetic energy is a maximum? No, we said it was a minimum. Acceleration is 0? No, we said it was a maximum. Speed is 0. Who said that? Total mechanical energy is 0. We just said that that's not going to be 0. That's going to be some constant non-zero number. And the potential energy is a minimum. No, we said that that was a maximum. For reference sake, these are good things to know about what goes on at a maximum amplitude. A ball swings at the end of a massless string as shown, and I want to know when the magnitude of the acceleration of the ball is the greatest. So we're going to get max acceleration at maximum displacement. Now we don't have a clever formula right now for what the forces acting on the simple pendulum are, but because it's undergoing simple harmonic motion, the same things are true at maximum position and at the equilibrium position. All of those things are still true in this case when we are at a maximum distance from equilibrium. So that means we're going to have maximum acceleration at a maximum distance from equilibrium. C is my equilibrium point. That force is equal to 0. D and A both represent maximum displacement. So A and D represent the places where the acceleration of the ball is greatest. All right, let's move on to some free response. A little graphical interpretation, a little graph sketching. It'll be a lot of fun. So the graph below shows the period of a particle undergoing simple harmonic motion. Sorry, it shows the position of a particle undergoing simple harmonic motion. So before answering the questions, what I would like to do is get all of the information that I can get from this graph. Right? So we'll do information about velocity in black marker. Velocity, because this is a position versus time, is going to be the slope of position versus time. We'll do the acceleration in red. That's the curve of x versus time, and if we remember, that's positive acceleration and that's negative acceleration. And then what we'll do, because this is position versus time, I can get information. I can get time for one cycle, which is the period. So those are all the things that I can get just by looking at the graph. Velocity, acceleration, obviously position, and period. So the first and easiest thing to get is the period. So if I want one complete cycle, that's half of a cycle. That is one complete cycle. So just looking at that right there, one cycle takes 10 seconds. Period is 10 seconds, just looking at that bit of information. Next thing we're going to look at is the velocity. I've got a positive slope here. So that means here, and a positive velocity. Up here, I've got velocity equals 0. negative velocity. Down here, 0 slope, velocity is 0. Here, positive velocity. Here, velocity is 0. Negative velocity, velocity is 0. Positive slope, positive velocity, velocity is 0, and so on and so forth. That's what I get just knowing my things about a velocity. Now, due to some other things that we know, all of these represent the maximum speed of my object. That's telling me how quickly my object is moving when it's going the fastest, because maximum speed occurs at equilibrium position. And that spot is the equilibrium position. The next thing that we're going to look at is the acceleration. The acceleration has to do with the curvature. Here we have kind of a straight line, so the acceleration is 0. Here, a bit of a frowny face, so we have negative acceleration. Straight line again, so the acceleration is 0. Smiling face, so we have positive acceleration. Straight line again, so the acceleration is 0. Which makes sense. At equilibrium, the net force is equal to 0 and the acceleration is equal to 0. And at our maximum displacement, the acceleration is a maximum value. We wouldn't expect it to be 0 right then. Also, because it's a restoring force, this is kind of a fun thing. That tells me that the force pulls opposite my displacement, which means my acceleration is opposite my displacement. So up here, I have positive displacement, but the pull is back towards the origin. So the pull is down, and for all we know, in the negative direction. And then over here, I have maximum negative displacement, and the pull again is back towards the origin. But for what we have drawn here, that's a positive acceleration. Those are the things that we can get from the graph right away without having to do any math. Let's see if that helps us answer any of these questions. What's the period of the motion of this particle? Well, we said the period, by definition, is the time for one cycle. And we saw very clearly that the time for one cycle here was 10 seconds. At what time will the particle first come to rest? Rest, velocity is equal to 0, and rest also happens when we are turning around. Both of those things happen at the same time. The first place we see our velocity equal to 0 is right here at the top. So looking at our graph, right there at the top is halfway between 0 and 5. We first come to a rest at a time of 2.5 seconds. At what time will the particle first reach its maximum negative velocity? So, maximum negative velocity, a couple of things that we know. My maximum speed occurs at equilibrium, so that means it's going to be a time of 5 seconds, 10 seconds, 15 seconds, and so on, because those are the times when my position graph crosses my time graph, where we said we were at equilibrium. But if I wanted to have negative velocity we need negative slope at equilibrium at the position equals 0 point. That only happens when time is equal to 5 seconds. My first maximum negative speed is right there where it's pointed down. At what time will the particle first reach its maximum positive acceleration? So positive acceleration is going to be concave up. And again, to reiterate a point, we get maximum acceleration at max displacement. But because of this whole restoring force idea, both the force and the acceleration oppose the displacement, right? So it's not going to be just at maximum displacement. What we're going to have is maximum positive acceleration at maximum negative displacement. And looking at our graph, that's exactly what we see. Maximum positive acceleration when we are down there at our lowest negative point. And that happens in between 5 and 10. So that happens at a time of 7.5 seconds. At what time does the particle first have its maximum kinetic energy? So, maximum kinetic energy occurs at maximum speed because we know that kinetic energy is 1/2 mv squared. So when the speed is the biggest, the kinetic energy is the biggest. We get our maximum speed at the equilibrium position where delta x is equal to 0. And because kinetic energy only depends on speed, direction is not important. It's going to happen as soon as we cross the axis again at equilibrium at time equals 5 seconds. That's the first place we have our maximum speed. That's going to be the first place that we have our maximum kinetic energy. All right, now we're going to get into some numbers. Assume the particle is a mass of 2 kilograms oscillating on the end of a spring. Calculate the spring constant of the spring. Okay, so because we're dealing with a spring, we know a couple of things. One of the things that we know is that the period of a spring is 2 pi on the square root of m over the spring constant. The other thing that we know is that the force of a spring is negative kx. Now, I don't have any information about force, so I can't really find k using this. So while that's true, that's not particularly useful at this juncture. What we're going to have to do is explore this whole period thing. For this motion, I know the period. 2 pi is a constant. They just told me the mass, and I need to find k. So in order to do that, I need to isolate k by itself on top. So the first thing that I want to do is get rid of that pesky square root. So we're going to square both sides. I've got t squared, but since I'm squaring both sides, I have to square everything inside of that term. Everything on that side. So I get 4 pi squared times m over k. Now I want to get k all by itself. I want to multiply and on top. So the first thing, the most important thing, is getting k on the top. We multiply both sides by k. So k times t squared is equal to 4 pi squared m. And then to isolate k, We divide it by the period squared. So we have to divide both sides by the period squared. So K is equal to 4 pi squared times the mass divided by the period squared. I wrote that down wrong. Divided by the period squared. So, plugging in our numbers, that's 4 pi squared times 2 kilograms divided by 10 seconds squared. So we can plug that into our calculators rather easily, and we end up with a K of 0.78 newtons per meter. Technically that's in kilograms per second squared, but since a newton is a kilogram meter per second squared, that's the same thing as a newton without the meters, so newtons per meter. That's my spring constant. Now that I have my spring constant, I can calculate all kinds of things. So, calculate the magnitude of the maximum velocity of the mass. All right, well, I know that maximum velocity happens at maximum kinetic energy. I also know that my energy is conserved here. So, that means my maximum potential energy will be equal to my maximum kinetic energy. Because we're talking about a mass on a spring, the maximum potential energy is 1/2 kx squared. Since we're talking about a maximum, it's ka squared at our maximum amplitude, and that's equal to my maximum kinetic energy, 1/2 mv squared. So, if we want the maximum velocity, we get rid of our 1/2. We already know K, so we divide each side by an M. M's go away, and my velocity squared is equal to Ka squared over M. So my velocity is the square root of K, 0.78 times the maximum amplitude. If you look up there, that's 3 meters squared divided by the mass of 2. You can plug that in and you see that our maximum velocity is 1.78 meters per second. That's my maximum speed. What is the magnitude of the maximum acceleration of the mass? Well, now we can finally get to information about the force. I know that acceleration is equal to the net force acting on my mass divided by the mass. Well, that's just the force on a spring, because that's the only force that's acting. So my acceleration is going to be kx over the mass. I'm not necessarily worried about the negative sign because it's asking about magnitude, which is just a fancy word for size. So, 0.78. Now, if we want a maximum, that means we have to be at an amplitude, which is times 3 meters, divided by the mass, 2. So, when we calculate our maximum acceleration, it comes out to be 1.17 meters per second squared. All of this from the basic things that we know. This wants a graph of the potential energy of the particle. Since we're talking about potential energy, what's important here potential energy is 1/2 kx squared. So that means my potential energy is going to follow what the position gives me. Looking at my graph, we do potential energy as a function of time. I saw that the position was equal to 0 when time was equal to 0. Since the potential energy has to do with the position, the initial potential energy is going to be 0. I would just plug that into the 1/2 kx squared. The next point of interest was here at 2.5 seconds. At 2.5 seconds, we saw that x was a maximum. And you can go back and look at that. That's my maximum displacement. That means I'm going to have maximum potential energy. So whatever that comes out to be, I don't really have any numbers, so we're going to stick it right there. And then at 5 seconds, my position was 0, so I'm back down. And then at 7.5 seconds, I'm at a maximum position, so I have my maximum potential energy back, and then this pattern repeats itself. We go down to minimum displacement at 10, back to maximum displacement. Now, what's important here is that because x is squared, potential energy in this case is not negative. It's always going to be positive. So looking at it, curved sections, flat sections. So there we go. That's how we would find our potential energy as a function of time. All right, second question, give yourself some time. And let's work through this one. So, in this figure, we have something moving towards a spring. Spring constant is given. It has an initial speed of 12. It hits the spring and oscillates in some. Calculate the kinetic energy of the block immediately after the collision. So, after the collision, there is no change in speed, no change in kinetic energy of the block. Because the spring is not compressed yet. There's no potential energy yet, so everything's still kinetic energy. This thing is still moving at 12 meters per second. So the kinetic energy, 1/2 mass times velocity squared, that's going to be 1/2 times 15 times 12 squared. So the kinetic energy here comes out to be 1,080 joules. Very simple. For the resulting oscillation, calculate the period. Okay, period of oscillation. Well, because we're a mass on a spring, the period is equal to 2 pi on the square root of m over k. Now, with this formula and the corresponding formula for a pendulum, they're given. You'll see on your formula sheet is a TS equals 2 pi on the square root of m over k. So we've got 2 pi on the square root of 15 divided by the spring constant, which is 200. We can easily put that in our calculators, and the period comes out to be 1.7 seconds. That's how long it takes for one complete oscillation. The amplitude of the oscillation. Okay, for the amplitude, and this is kind of an important point to make. The amplitude is an energy question, and so when we're talking about energy, the best place to go with that is the conservation of energy, knowing that the maximum potential energy is equal to the maximum kinetic energy. So maximum kinetic energy takes place at equilibrium when the spring is uncompressed. That's our energy way back in part A. So, because we're talking about mass on a spring, the maximum potential energy is 1/2 K amplitude squared is equal to 1/2 mv squared. We don't have to do that. Is equal to the kinetic energy we had before, 1080 joules. So my amplitude is 2 times 1080 divided by 200, my K, square rooted. Putting that all in there, my maximum amplitude comes out to be 3.28 meters. I have a period, I have a maximum amplitude. I want a free body diagram for this mass on a spring. So, this is what we had, right? This was what my mass was moving towards this thing, and it hits the spring. So when we're at equilibrium, the spring is not compressed yet, so that means there is no spring force, and for whatever I draw, the net force had better be equal to 0. That's what's going on in equilibrium. Since there's no spring force, there's not going to be any forces to the right or the left, and nothing happening there. I do have a normal force that's up because we're on the surface, and I have a weight that's down. And since we're always going to be on this surface, we've got a normal force that's up, a weight that's down, a normal force that's up, and a weight that's down. It's important not to forget those things. When the spring is at maximum compression, we're over here. That's part 2. We've compressed that spring as much as we can. So at that point, the force of the spring is pushing me in that direction. I've compressed it, so my delta x is in that direction. The spring is going to push in the opposite direction, like we have written. And then when the spring is at maximum stretch, that means we are going to be kind of out here where this was my equilibrium position. And so my stretch is in this direction, and my force is restoring me back towards equilibrium, so it's pointed to the right. Okay. Calculate the magnitude of the acceleration of the block. Well, acceleration is the net force over the mass, and since it's a magnitude, I don't really care about the direction. So it's kx, since we're talking about maximum, spring constant times the amplitude divided by my mass. Well, spring constant is 200. My amplitude is 3.29 meters. That's divided by my mass of 15. So that maximum acceleration comes out to be 43.9 meters per second squared. Kind of using those same ideas that we used from the first problem. Now, plot the velocity as a function of time for 2 complete oscillations. And then right is to our left. Graph ended up coming down here. So we want velocity as a function of time. We have to change these axes because it doesn't quite work. So let's just say, care about that. -15 meters per second up there. -15 meters per second down here. Based on the picture that we had going on, based on when we start timing it, we begin moving to the right. And we're going to say that time equals 0 at the time of the collision. Well, at the time of the collision, Our little picture shows us moving 15 meters per second to the right. So initially, I have positive 15 meters per second worth of velocity. We want 2 complete cycles. So I know that I am going to again be at the equilibrium position for 1 complete cycle. Again, moving at positive 15 meters per second. I've compressed it, I've swung back, and I've recompressed it. That's 1 complete cycle, which means I'm going to get 15 meters per second somewhere in the middle there as well. And from what we did before, I know that the period is 1.7 seconds. So I know I'm going to be back here at 1.7 seconds at positive 15 meters per second. So if we're looking at this little squiggle that I made up here, right here is time equals 0. Here, time equals 1.7 seconds. And right there is time is half of that. Draw a little arrow. Time is the period over 2. 1.7 divided by 2, 0.85 seconds. But if we look at it, here I'm moving this way. Slow down and stop, and then I begin to move this way. So at 0.85 seconds, halfway through, I am moving, but I am moving with a negative velocity. So that's 1.7, 0.85, somewhere in there. And then that whole cycle repeats itself. So, oh, missed it. So that's 1 cycle. The next cycle, 0.4, we're going to be back here at again 1.7 seconds, and then halfway in the middle of that, we're at a negative velocity. So kind of extreme, but our velocity versus time looks like that. Okay, that's our session. Thanks for listening.